Questions 18 to 23. So we're talking about benzene in the formula, and it's C6H6. And okay, so they're talking about possible isomers. And so, of course, in your mind, you should have that an isomer means it's the same molecular formula, but there's a different arrangement of atoms. So you should have that clear in your mind. And there's many, many different types of isomers. There are stereoisomers, which are concerned with the three-dimensional arrangement of molecules. And there will be questions on that. You can be rest assured. And then there's structural or constitutional isomers. And this is what they're starting to talk about here, structural or constitutional isomers. And these are isomers that differ by the arrangement of atoms or bond, or even the bonds, the types of bonds, as you can tell, because look at the different structures, and the types of bonds are very different, double bonds, triple bonds, single bonds, and yet they all have the same formula, C6H6, that's the whole point. And there's a subdivision of structural or constitutional isomers, which is where you only change the position of an atom or group. And those are called positional isomers because you're only changing the position. And this is also a number of questions here are related to positional isomers. So, and it's also important that you ACER usually will give you, if it's going to be a long passage and they know you're going to have to use the same concept over again, then they'll give you an example. And so they do give you an example, and they tell you that there's only two possible isomers for the monosubstituted product of structure 1. So if you don't get that, then it's going to be a problem. So it's very important that during the exam that you look at the example that they provide, make sure you fully understand the example that they provide so that you can then start applying that to other questions. So the molecule structure 1 is what I drew. Of course, in organic chemistry, we don't have to draw the hydrogens. So you have a double bond there, and we're told that there are just two possible isomers for this, for a monosubstituted, meaning we substitute for something. So let's substitute for X, okay? We substituted X for a hydrogen, removed a hydrogen, put X there. And so that's one possibility, of course. And then this is coming across, this is a double bond up here, double bond up here. And this is another possibility, which is the X group comes out here. So you can see that it's the same number of atoms. We just changed the position of one. So it's a positional isomer, but you can call it a constitutional or a structural isomer. And we can see that these are two different molecules because this is bonded to a carbon that is double bonded. This is bonded to a carbon that has single bonds. So no double bond. So these are definitely different structures. However, this structure is the same as, say, I didn't draw this here, okay, and I drew an X here. If I draw an X here, you might say, oh, they're mirror images of each other. Yeah, but they're superimposable because I can just take this molecule, flip it on the other side, and they will be the same. Now, I know you might be saying, how could you just flip it? Isn't this going up or down or something? And won't they be going the different ways? No, because this is flat here. This is flat because when carbon is in the center of a tetrahedron, which means 4 different bonds, some of those bonds are coming towards you or away from you or whatever. But when carbon is double bonded, right away, that means it's in the center of a flat triangle. And we call that trigonal planar arrangement. And so if carbon is here, this is just an X group coming out here. So that means I could just take this, flip it on the other side, and it would exactly match that same molecule. And likewise, if I if I put an X group down here, I can just turn this and it would be that. If I put an X group over here, down here, I can just turn it and it can be that. So no matter where I put an X group, it could be that. And likewise, for the other molecule, if I remove the X group here and I put it on the other side, then it's the same as this molecule as written. So these are the only, removing this. So these are the only two mono-substituted, okay, just one substitution molecules of structure 1. And so once you understand that, then you can start playing with the different questions that they have. So question 18, consider structures 2 and 3. How many different mono-substituted isomers, so we're going to replace hydrogen for whatever, iodine, can be produced from them. So now looking at the structure, it goes something like this. And I'll just put a carbon here just for clarity. So we can put the different places that where we can put a hydrogen. We can put one here. Okay, we can put or an X group or halide. We can put one there. We can put one here, and we can put one here. Those are the places where hydrogen lives. So those are the places that we can replace in this substitution reaction. So I'm not saying do them all at the same time, okay? Because I just don't want to draw it 3 times. But one substitution would look like that. Another substitution would look like this. Okay, so that would be the substitution. And another substitution would look like that. Now you might ask, okay, but why don't we have a 4th substitution with an X group down here and a 5th with an X group down here? And it's because if you were to put a substitution down here, it would be identical to having this substitution up there. For the same reason that I described before. These are flat bonds. And so flipping them upside down, flipping them on the side, you get the same arrangement of molecules. So putting one here and here is just the same molecule. It's not a new isomer. These would be the 3 possible positions in order to create 3 possible isomers for that structure. And now for structure 3. Well, structure 3 does require a little bit of imagination. Okay, so you can see that structure 3 is like having, okay, the best place to focus on is the way I drew it is by looking at the square in the back, because that square in the back is exactly this square here, which is exactly this square here. It's the identical shape of that. So that shows you how everything is there's a certain symmetry, of course, with the way that this is created. So if now these are mono-substituted, so if we put just one group here like that, then having it here would be the same if I just turned it, like if I turn this around like this, just turned it around, then it would be the same as having an X like that. And then if I turned it around again, it would be as if, or it was if I'm bringing the X group up here. Or if I just turned it this way, like the way it is right now, and I just turned it like that and brought this X group to the front, then it would be the same molecule. And then if I bring this thing and I put it upside down, it would be the same as having an X group down there, or an X group here, or an X group there, just by moving and rotating it. In other words, with just one substituent, it's always the same molecule, no matter how I maneuver it. I can't move it into different places and have a different result. Okay, so that is for question 18. That is that there are 3 possible monosubstituted isomers for structure 2 and only one possible for structure 3. 19. How many different disubstituted isomers can be produced from structure 1? So here is structure 1. Thankfully, we have it already. And so how many disubstituted? So that means with 2 substitutions. Okay, so I'm going to put, I'm going to just use a different color. So this is my first substitution is here, as you see it already. So I'm going to put my second substitution over here. Now, can you see that if I chose to put my second substitution here, okay, that molecule is different from this molecule. This molecule has 2 X groups attached to carbons that are double bonded. This molecule has 1 X group attached to a double bonded carbon, 1 X group attached to a single bonded carbon. Different. And can you see that if I were to put the X group over here instead, that this is another different molecule because the X groups are on opposite sides. And then, carrying on, if you put the X group here, this is yet another option, another possibility. And putting the X group here, that's even different because clearly having the X group close to this other X group on this side is different from having the X group way on the other side to this one. So those are all different molecules. So we have 1, 2, 3, 4, 5 different disubstituted just by doing it that way. But we already saw that there was another way to have a mono substituted, and that's when the X group instead of up here is down here. So what disubstituted can we do? We put the X group here. We can put try putting the X group right across. And then this would be a new one right here. So this would be 6. You might wonder, well, can't we put the X group down here? Yeah, we can put the X group down here. But then that would be exactly like one of these. And if we put the X group here, it would be like one of these again, or there, or whatever, because we've done all that already. So putting the X groups in opposition to each other, that creates a new possibility. And so there are 6 different disubstituted isomers for structure 1. And the answer for 19 is D. Okay, so question 20. If it was found that just one monosubstituted isomer and just 2 disubstituted isomers could be prepared from benzene, this would be consistent with benzene having, okay, so one mono. Okay, so structure 2 only. Well, it cannot be structure 2 only because structure 2 we have already seen for a monosubstituted can have 3 different monosubstituted structures. So A is incorrect. Structure 3 only. So structure 3, that's true that we have seen that it can have only one monosubstituted. So now we have to see how many disubstituted it has, because that will let us know. Because the question is asking for 2 disubstituted. So let's check that out. So here's one. Now we can add a substituent down here. Okay. So here's one place that we can add a different group. Now pretend that we don't add it down there. We add it down here instead. Now, can you see that these are 2 different positions? Because in this position, it is got a single bond directly to it. In this position, it is opposited. So these are definitely 2 different types of stereoisomers. Then we can put it down here. So this is a third possibility. And let's see. So we have at least 3 that we can see. I'm just trying to see if I can imagine putting one there. Huh. Yes. Sorry. Sorry. Yes. Okay. I can see that it's different. That that is different from that. And sorry, it took me just a second. But it's because this one is up in the triangle. Let's imagine it that way. And then this one is down in the square. Like it is in a triangle, but it's not sharing the same triangle as this one up here. So then we have 1, 2, 3, 4. And in fact, two of them, okay, I'm just going to try to minimize the ways that I'm going to draw these things, because that first time I drew it there, I've never drawn anything that well in my life. So I'm very afraid about having to redraw this molecule. Okay, so I am going to have to draw it a little smaller, like that. Now this is one of the isomers, okay, because look, if that's what I just redrew, okay, I guess I should put this out of the way. Okay, so I just redrew that molecule. You can see it's the same. Okay, but I redrew it to show you this. Do you notice that these are mirror images of each other? Okay, I guess I have to move my hand a little more. So look, those are mirror images of each other. It means that if I were to drop a mirror down the middle here, like that, okay, these would be mirror images of each other. Now I've got a hard thing for you to do, and that is that I want you to imagine trying to move the molecule on the left and rotate it to see if you can superimpose it on the molecule on the right. You can't do it. These are non-superimposable mirror images of each other, or enantiomers. And so, but anyway, that's not what the question was about. But I just wanted to show you that there are many different isomers for structure 3. So B is wrong. And so we look at structure 4. Structure 4 is easy for me to draw. And it also brings up another important teaching point. I hope you don't mind when I take a little moment to add some content to your mind, because the reason I do it is because I know that there are other related types of questions that they can ask on the exam, because they're not going to repeat exactly what you're seeing. So I need to, well, I would like to help you for that. So here we have another isomer of C6H6. So we're going to look at how many mono-substituted we can make of that. Mono-substituted, so we remove one hydrogen and we put an X. So we remove one of the hydrogen and put an X. Can you see that by putting it here at this end of the molecule, it's identical to as if we put it on this end of the molecule, because this is a flat we can just twist the whole molecule onto itself and it would be the same thing. So it's not as if there was a hydrogen in here somewhere where you can put in a substitution and then you can have all kinds of differences. We can only remove the hydrogens. Hydrogens are the least important atoms in organic chemistry, in one way at least. And so they are being substituted here. This would be the same if it's on either side. So there's only one mono-substituted isomer that is possible. I also just wanted to mention something. All these bonds, when you see carbon bonded 4 times, the carbon is in the center of a tetrahedron when it is bonded to 4 different atoms. Sometimes it's restricted because, like this, but in a normal saturated carbon, you will see carbon in the center of a tetrahedron. The bond angles are 109.5 degrees. These are sp3 hybrid bonds. When you see carbon It's double bonded. These are sp2 hybrid bonds. As I said before, carbon is in the center of a triangle, a flat triangle, trigonal planar. And when you have carbon, which is triple bonded, these are sp hybrid bonds. This would be 180 degrees because it's a flat line. This is a triangle, 120 degrees bond angles. And these are sp hybrid bonds. So these are just things to keep in the back of your mind, because sometimes these types of questions come up, or you have to use that kind of knowledge for the exam. So there's only one monosubstituted. Now we just have to find out how many disubstituted there are. Well, one disubstituted would be if we put 2x groups on this carbon. Now, having 2x groups on this carbon is identical molecule to having 2x groups on this carbon, because it's just flipping the whole molecule around. So this would be one isomer. The other isomer would be CC123. Oh boy. Yeah, 1, 2, 3, C, 1, 2, 3, C. Okay. The other one would be if you had this, because you're just trying it. You're on the exam, you're trying it. You look where the hydrogens are. You just replace 2 hydrogens on one, and then you replace 1 hydrogen and 1 hydrogen. That's it. I mean, this is the same molecule. You flip it or you don't, but there's nothing else we can do for substituents. There's no other hydrogens hiding anywhere that we can substitute for. So these are the only 2 disubstituted isomers that we can create for this compound. Therefore, the answer would be structure 4 only. 20 is C. Consider these 4 trisubstituted isomers of structure 3 with the formula blah blah. Which of the following is correct? Okay, so I guess the first thing that I want to say is free your mind. Okay, I want you to be able to notice, how should I draw this? Okay, so what I would like you to notice is for the first one, you have a group here, a structure 5. You have an X group here, an X group here, and then an X group here. So the 3 X groups, they make an L shape. Okay, so please remember this L shape. Okay, that's the connection that these groups have. Now look at number 6. Number 6, and remember, this is a square. This right here is square. This is the same shape square as the square in the back here. Same shape, okay? It's just the angle at which you're looking at it. So this is the perfect square here, all right? And so if you look at structure 4, you will see that the relationship of those 3 X groups also makes an L. The L is upside down, but it's okay. And the L is right there on the box, on that square box. So it's okay that it's upside down, because I already said before, you can take this and you can rotate it and move it upside down, sideways, or whatever way you want. Not sideways, because we're not comparing them sideways, but you can certainly do it upside down or turn them around. So structure 6 and structure 5 are equivalent structures. They're the same structures. We're just looking at it at a different angle. Now, structure 7, there is no L in 7, because structure 7 has one group back here, it has another group back here, and it has another group in the front here. So it doesn't have that L where, because look, this is an L where it's touching each group in the L. Here, if you try to make an L, you have no group here, then you go there. No group, then you go there. No group. There. So here it's 3 groups in a row in an L. And that's true for structure 5, structure 6, but not for structure 7. Then look at structure 8. You can even pause and see if you can figure it out. And notice that you do have in structure 8, you have one group here, you have one group here, and you have one group here, and it makes that L in this square here, it makes it L going upside down right there, continuous. So structure 8 is also equivalent. So 5, 6, and 8 are equivalent, but 7 is different. So the answer to 21 is B. Moving on to 22. How many different trisubstituted isomers can be produced from a structure number 4? So here we have structure number 4, and we have the disubstituted there. I'm adding another substituent because we had one extra hydrogen still here. So I'm permitted to replace that hydrogen. And when I do replace that hydrogen, then we're left with no hydrogens on this carbon, just 3 X groups, and then it's connected to this carbon. So this is one trisubstituted product that I could imagine. And then another trisubstituted product would be if you had a, sorry, I put a hydrogen. If you had an X group here, so you connect an X group here, and then the other X group is on the other side. So this would be a second isomer. But you might be thinking, okay, now let's try an X group on this side. But it's the same as what we already have. Oops, I'm sorry, I fell off the screen. So so we have 2 on this, we have 1 on this, and if we were to take this X group and bring it over to the other side, it would be the same as this molecule that's there already, because you would just have turned it around. So that's so that means, and there's no other choices we have. There's no other substituents that we can try. So it means there's only 2 different tri-substituted isomers possible for this, and so 22, the answer is B. Now, question 23. Stereoisomers are molecules that are mirror images of each other, but that cannot be superimposed onto each other. So, of course, these are the 3-dimensional arrangements. Consider disubstituted molecules of structures 2 and 3. Stereoisomers would be possible for disubstituted molecules of, well, going back to structure 2, okay, so this is structure 2, and it's important for you to look at this and to know that in order to have a stereoisomer, well, there's different types. There are enantiomers and there's diastereomers, and to be an enantiomer, you need to, or an optical isomer, you need to have a chiral carbon, and that is a carbon that's bonded to 4 different substituents or groups. And here, in this molecule, you will never find a chiral carbon because every single carbon is bonded twice to another carbon. So it's not bonded to 4 other groups. Bonded twice to another carbon, this carbon, bonded twice to this carbon, this one bonded twice to that, and then these 2 carbons bonded twice to each other as well. So there's no chiral carbons in structure number 2. So structure number 2 cannot have a stereoisomer. It's not possible. Then for structure number 3, I already showed you that structure number 3 does have 2 non-superimposable mirror images of each other, and because of this, structure 3 does have a stereoisomer. So the answer would be B for 23.